Hello and welcome to E233. I'm your instructor, Gregory Myers. In this video, we're going to take another look at our sample P3. This one is based off of our physics projects. This video assumes several things. Number one, that you have completed your P2, which was also based off of our physics demo, as well as having started your P3 and having triaged your switches per the description in our P3 instructions, and that you've also obtained a copy of your P3 setup, which included the function prototypes, as well as the stubs of the function, and your P3 sample.txt, which does not look too terribly different from your P2. In this video, what we're going to do is we're going to focus on building the functions themselves. And what we'll do is we'll push the testing off to a later video. So to begin with, what we want to do is we want to take a look at some of the minor changes that I've made in our P3.c between the last video and this video. And you'll want to go ahead and update yours as well. Particularly, I've went ahead and modified the comment block at the top of the file to include the current date and my email address if you have any questions. You'll also see that I have added a couple of includes for string.h and ultimately for math.h, which we will be using when it comes to the sine and the cosine functions in our 2D problem, as well as updating the comment block for main and for each one of our functions. Now, taking a look at the functions, you'll notice that I am accepting a double y int. In other words, the input for the projectile 1D will be the initial height. My input for projectile 2D will be the initial velocity as well as the theta, and the input for the simply supported beam will be W, which is the load applied, the length, which is the length of the beam, and A, which is the location of the load on the beam. You'll also notice that in the comments, I have mentioned the return data type integer, which will indicate success or failure. Now, we're not going to do a terrible amount of logic in this one. As a matter of fact, we're actually going to be doing no logic or no validation. We'll push that off to a later video. So instead, our functions are going to be rather naive or rather optimistic in that they will simply assume success no matter what. Once again, we'll come back to that concept later on. So to begin with, let's focus on our Projectile 1D version 2. And the first thing that I want you to do with all of your functions as you're building these from more of a top-down perspective is simply put a print statement at the beginning of each function indicating that the function is running. And so in this case, what I'm going to do is I'm simply going to specify that we are running Projectile 1D version 2. Basically, all this is this is a friendly message that indicates that the function is in fact running. This will greatly help when it comes to troubleshooting, but also what it'll do is it'll give some confidence to your user that your application is working, particularly as you start getting with larger applications. Now, let's focus on the problem at hand. And to do that, we'll probably need to go back to the instructions for our P3. And if nothing else, go back to the PowerPoint that I provided for you in the earlier videos. And we also have our P3 sample. Now, between those, we should recognize that the problem is essentially the same as our P2, which means that for our initial one-dimensional problem, we simply calculated the T final from the initial height. So what we want to do is we want to go through first and we want to declare all of the variables that we're going to need, and perhaps even a few extras that we could use to expand the problem later on. But we also want to specify the units associated with each one of the variables. So the data types, the variable name, and the units. And so what we'll do is we'll start off with our Y final. So it's going to be a double Y final. This is going to be in feet. We'll also have a double for our T init, even though we're going to assume that it starts off at 0 seconds. We're going to have a T final, which will also be in seconds. We want to calculate our VY final, and we're also going to make the assumption that the VY init, which will be in feet per second, will be 0. And as I said, we're going to calculate our VY final, which would be the velocity essentially right when it hits the ground, also in feet per second. As always, after we declare these, we must initialize them. And so we will simply initialize our Y final equal to 0. Our T init, which is essentially when our stopwatch, our timer starts, will be 0. Our T final will be 0. Our VY final and our VY init will both be 0 as well. Now, a couple of things that probably bother you already at this point is that particularly I am ignoring my Y init. Well, because it's being passed as a variable to the function, I neither have to declare it as a separate variable inside the function, nor do I even want to initialize it. In other words, if I come down here and I initialize my Y init, then effectively what I'll do is I'll overwrite the value that the user is providing to us. And then the second thing that should bother you a little bit is the fact that I am initializing variables that I will ultimately use in a calculation. For example, our goal here is to actually calculate our T final. Now, it's just a good habit to get into to initialize all of your variables after declaring them, because later on, if we have some sort of logic in our function, we could wind up in a situation where we accidentally end up using a variable that we thought we were going to calculate, but we also failed to initialize it, and then you'll have some unpredictable results. So short story, just get into a habit for now to initialize all of your variables. Now, moving forward here, we want to go ahead and calculate the values. And what we're going to do is we're going to start with our T final. Our T final is going to be the same as before. It's going to be off of the square root, or calculate off of the square root of -2 times our Y init, in other words, the initial height, divided by our AY. Now, you're probably going to get an error at this point. Specifically, it's going to be one that says that you don't have an AY, which is probably a good opportunity for us to go to the top of our source code and add a couple of defines, much like we did in our earlier project. And so in this case, what we want to do is we want to have an AY that is going to be a -32.2. And as we did earlier, we also want to specify the units. In this case, it's going to be feet per second squared. We can go ahead and do the same thing for our AX. And in this case, it's going to be 0 feet per second squared. Now, you'll note a couple of things here with the defines, that you do not need the semicolons, but also when you scroll down, you'll see that now you no longer have an error. Now, the AX is in some cases somewhat optional. Once again, my goal here is that I want to sort of expand out this to be used later on. And so you'll see that we'll use the AX in our Projectile 2D version 2. I sort of, in this case, know where we're going with this because we've already completed our P2. Now, we can go ahead and calculate our VY final. And our VY final is just simply going to be based off of our VY init plus the AY times the T final. Once again, these are just simply based off of the physics equations that I've provided for you in the PowerPoint. For your project, it might be a little bit different. We might be doing a different, maybe a chemistry project or a geometry project. So in other words, just look to the source material, but fundamentally, this is all going to be the same. And then lastly, what we want to do sort of as a validation is we want to go ahead and calculate our Y final. Now, we know it should be equal to 0, but this gives us a good validation that our formulas are in fact correct. And so we'll just go back to the position equation. So it's going to be our y init plus vy init times our t final, and then plus 0.5 times our a acceleration in the y direction times our t final squared. And there's a couple of ways that you can go about doing this, but I'm going to go ahead and use the POW function, and I'm going to square it. At this point now, it's time for us to go ahead and display the output. And here is where this sample text file comes into play, as well as our earlier P2 project. Basically, our goal is just simply to make the output look nice for the user. And so to do that, we'll start off with a printf, and you can just go ahead and borrow the text from my sample file. But once again, I'm not looking for a specific number of spaces, rather that you just have nice looking output to present to the user. You can also do the same thing with the horizontal bars. In this case, I've made them out of equal signs. The idea is we can, once again, just make this look nice for the user. And then while we're at it, let's go ahead and put the bottom bar on the table. And this would be a great opportunity for us to save some work by simply copying these three print statements into Notepad, and we'll use these on our other functions just as sort of as a template. So I'm going to move this out of the way, and then let's focus in on our 1D problem. And you can see I provided you with somewhat of an order with the output arguments or the output table. The idea here is that I first display the values that I've collected from the user, or the ones that I've initialized or made some assumptions on, and followed up with then the calculated values. I'm not too terribly worried about the order in which you present these. Once again, just have some sort of solid logic behind them, and then include all of the values. All right, so what we'll do here is we'll do a preliminary lineup. We'll focus on our y init, which was going to be in feet. I like to follow this up with a colon, and then I simply tab it over and align it up with the value column header. Now, at this point, you're going to have a little bit of flexibility in how you display the value. For this particular example, we're going to use the format spec of %8.4 followed by a new line, and we're going to plug into this our y init. And now you'll want to look to the specifics of your current project to know what the format spec is that I'm looking for. But the idea here is that I would have a total of 8 spaces allocated for the output, with 4 of them going to the decimal values, or the numbers to the right of the decimal point. All right, so we'll follow up with this with our y final. That is also in feet, and a %8.4. As a matter of fact, you could probably save yourself a little bit of time by copying that and simply pasting it as needed. And there is going to be our y final. Then we want to have our t init, which we have initialized to 0 seconds. Whether you do SEC or S is perfectly fine. Once again, 8.4. I accidentally left off the F here. Let's be a little more careful. It's 8.4 F. And then our t init, our t final, once again in seconds, %8.4 F, followed by a new line. And this will be our t final. Our vy init, which will be in feet per second, percent 8.4 F followed by a new line. This will be our VY init. And then lastly, our VY final, which is also going to be feet per second. And for that placeholder goes the VY final variable. Now, at this point, we've actually written a pretty significant amount of code, so we probably want to go ahead and build it just to make sure that we have not introduced a bug. If you write too much code between your builds, then it's going to be harder for you to track down problem. My recommendation is if you've done work on perhaps a function or maybe no more than about 10 lines of code, probably a good point for you to go ahead and build and fix what you've got so far. Now, what I'm going to do is I'm going to reserve testing of these functions to another video. So what we're going to do now is we're actually going to go ahead and assume that this one is working, which might be a false assumption, but we're going to move on then to our Projectile 2D version 2. Part of the reason why I'm doing it this way is because I want us to look at the pattern between our P2 and our P3 and assume that if you've got your P2 working, that you can also get your P3 working. The main change here between the P2 and P3 is the elimination of some of the local variables. In this case, you'll notice that I am not declaring nor initializing my y_int. And so you can probably guess that we're going to be doing the same thing in our Projectile 2D version 2, with the significant difference being that I'm going to essentially not be declaring and not initializing my v_init and my theta. So at this point, what I'd like to do is I'm going to go ahead and pause the video. I'm going to give you an opportunity to build your own 2D version 2, and we're going to discuss the differences, and we will go from there. Welcome back. So here we are in our Projectile 2D version 2. Hopefully you've had some success at fixing your Projectile 1D version 2 and have been able to also successfully write your Projectile 2D version 2. Once again, we're looking at the differences between our P2 and our P3. You'll note that I essentially have the same list of local variables that I had in our P2, our t_init, our t_final, our y_init, and our y_final, and then our x_init and our x_final, because we are looking at this problem now in 2 dimensions. And I have also provided temporary or local variables for my vy_init, my vy_final, as well as my vx_init and my vx_final. What is missing, however, is the v_init and the theta, because once again, these are provided to our function. And so we do not want to declare them, or do we want to reinitialize them or essentially overwrite the values that the user has passed. And so the next step here is to simply initialize all of the variables that we intend on using, because otherwise we can't trust the values. Do so even though we may end up using these values in calculations later on. In other words, you technically could skip the step of initializing your vx_init and your vy_init because we are so closely following them up with assignments. But once again, it's a good habit to get into to simply initialize all of your variables. That way you're relatively sure you won't have a problem later. Now, moving on, we simply split the v_init into its horizontal component and vertical component by using cosine and sine of theta. Remember that theta is in radians. And so we now have our vx_init and our vy_init. If we recall from the physics formulas, you'll know that the T final is based solely off of the V, Y init in this particular setup, because we're making some assumptions, particularly that we are on horizontal ground and that we do not have some sort of propellant. In other words, that our acceleration is constant, which brings us then to our X final and our Y final, which are simply calculated from the position equation. And you'll note here that I have used my AX constant that I have defined at the top of our source code. You'll see that these two formulas are fairly similar. In other words, just simply the variables themselves are different, but fundamentally they're both based off of the position function. Likewise, you can calculate our Vx final and our Vy final. And once again, I have put together a table based off of the sample text that I provided, as well as having borrowed from our little notepad here, where I've used it just basically as a temporary place to copy our table template. And at that point, we should be done with our Projectile 2D version 2. Once again, before you go any further, I encourage you to go ahead and build it. And as I said earlier, we're going to focus on the testing of these functions in a later video. For this particular project, I want you to go ahead and move on to your beam, or rather for this particular video. So I will come back and see you guys in just a little bit. All right, welcome back. So hopefully you've had some success with your earlier two functions. Now you're looking at the simple supported beam, and the differences between the one that we saw in our P2 versus this one is that we once again are not declaring the variables that are being passed to the function. In other words, basically we do not declare local variables for W, L, and A. We're provided them by virtue of our function signature. And so all we have to do is declare then our reaction forces R1 and R2, both in pounds. We're going to initialize only those two variables because, as I mentioned earlier, you don't want to initialize or overwrite the values that were provided by whoever called your function. We calculate the values once again based off of the physics formulas that I provided for you, and we print out a nice looking table once again based off of that template and the sample output that I've provided. Now, once again, you'll notice up here at the top of our function is a print statement, just indicating that we are calling this function. Like I said, that's just meant to provide some friendly communication back to the user of your application. And you'll see in the later video when we test these why this is very beneficial in verifying that your program is running structurally correct. In other words, we may still have issues with our formulas, but at least that the functions themselves are being called once we provide the correct switches. So I'm going to go ahead and stop this video here. And in the next video, we're going to focus on how we're going to set up our main so that we can collect values from the user, both interactively and parametrically, and then pass those values to these functions. As always, if you have any questions, comments, or concerns, don't hesitate to reach out. And thank you for watching.